In this video, we're going to be talking about derivatives of exponential functions. And before we get into this video, there's one fact from our previous video that we need to remember really well to make this video go smoothly. That fact is the value of ln of E. So ln of E is equal to 1. And if you wanted to figure out why that's true, we could flash back to our discussion around logarithms. Remember that ln just means log base E. So we're trying to find log base E of E. In other words, we're saying what exponent do we put on E to make E? And the answer would be 1. So if we can remember throughout this video that ln of E is equal to 1, then that will be super helpful. Well, today we're focusing on exponential functions. So an exponential function looks something like this. B is a constant, x is a variable. So you've got something like 2 to the x, or 3 to the x, 7 to the x, or e to the x. Those are all exponential functions. And we want to figure out how to take the derivative with respect to x of a function that looks like that. So here's the formula. You go ln of b times b to the x. So let's try a quick example to practice this formula. We're going to find f prime of x, and for part A, our function f of x is equal to e to the x. So according to our formula, we're supposed to write down ln of e times e to the x. Okay, so imagine we had e to the x times ln e. Well, the idea is that ln e is 1, so that would just cancel out and you'd have e to the x as your derivative. Now, if you look at part B here, and you've got a function to some other base, let's say instead of e to the x is now 3 to the x, then our derivative is ln 3 times 3 to the x. So we can see why it's really nice to be working with base e in this situation, because with base e, your derivative looks like e to the x times ln e, and that ln e just cancels right out. Whereas with any other base, you get essentially this little correction factor on there, ln of your base times whatever your original exponential function is. So this is why base e is the most convenient base to work with when we're dealing with either exponential functions or logarithms. And the function e to the x is used throughout science and engineering for a variety of different applications. The second formula that we're going to be using helps us figure out how to apply the chain rule when we have an exponential function. So I'll put a star beside this one, put a star beside the top one as well. So these are our two formulas for this video. And let's look at this bottom one here, the chain rule for exponential functions. So imagine that you have a function like b to the u, where b is just some constant and u here is some function of x. So this could be something like, say, 2 to the x squared, or e to the sine x, or something like that. So you've got a constant base, and then your exponent somehow involves x. We want to figure out how to take the derivative of a function like that. So the formula is you take ln b times b to the u, and then you multiply by du by dx. So what this is doing, this is taking the derivative of the outside function being the exponential function, and then you multiply by the derivative of the inside function, which is actually your exponent. This is a little strange, feels a little weird that the exponent would be the inside function in this context. So let's talk about exponential functions in more detail, and we'll understand why the exponent is actually the inside function. So in some textbooks, you might see e to the x written as exp of x. I would say exp of x is sort of a long-winded way to write it, so I usually prefer the shorter notation e to the x, but there is one convenient thing about this notation, and that is that it makes it very clear that the inside function is actually the exponent. That might become even more clear if you wrote something like e to the x squared. In this sort of old-fashioned notation, it would be written as exp of x squared. And when you write it like that, then it seems more obvious that the actual exponential function would be the outside function, and whatever's in the exponent would be the inside function. So this is really how we want to be thinking about it when it comes to our chain rule. Because again, if we go back to our chain rule, it's saying take the derivative of the outside function, which is the exponential function. So we do this part first, and then multiply by the derivative of the inside function, which is the exponent. So although we won't use the exp notation, just because it's kind of clumsy to write down, it is handy for reminding us why the exponent is actually the inside function. So with that, we're ready to practice some chain rule calculations. So we're going to be taking derivatives of things like e to the x squared, and I think just right up at the top right corner here, I might write down our formula. So if we want to take the derivative with respect to x of something that looks like b to the u, we take the derivative of the exponential function first, which looks like ln b times b to the u, and then we need to multiply by the derivative of our inside function, which is the exponent. So then multiply by the derivative of the exponent. Okay, so let's put that into practice here. So we take the derivative of the exponential function by going ln e times e to the x squared, and then we multiply by the derivative of the exponent, which is 2x. And this works out really nicely whenever your base is e, because remember that ln of e is just 1. So we would get 2x times e to the x squared. Part B, let's try taking the derivative of something like 2 to the root x. So if you prefer, before you take your derivative, you could just rewrite your function. You could say that's like taking the derivative of 2 to the x to the 1/2. So x to the 1/2 is our exponent here. And that might make life a little bit easier when we get down to our chain rule. So the outside function is the function that goes 2 to the blah, and the derivative of that is ln 2 times your original exponential function, so 2 to the root x. And then we need to multiply by the derivative of what's in the exponent. So derivative of x to the 1/2 is 1/2 x to the minus 1/2. Okay, and then we can just think about how to rewrite that a little more clearly. So you could write 2 to the root x times ln 2, might be a little easier to read if you bracket it like that, and then on the bottom we'd have 2 coming from the 1/2, and the x to the minus 1/2 would send a square root into the denominator like that. All right, let's find the derivative of e to the x plus 7. So we first deal with the outside function, which is the function that goes e to the blah. Our derivative is going to be ln e times our original exponential function, and then we multiply by the derivative of whatever's in the exponent. So derivative of x plus 7 would be 1. Okay, that works out really nicely because ln of e is 1. We have this other factor of 1 at the back here. So the answer would just be e to the x plus 7. Okay, and then finally, let's try a product rule. So we're going to take the derivative of x cubed times e to the root x. According to our product rule, we'll take our first factor, x cubed, multiply by the derivative of our second factor. So that's going to look like ln e times e to the root x times the derivative of what's in the exponent. Okay, so our exponent is root x, or you could say that's x to the 1/2. Derivative of that 1/2 x to the minus 1/2. So that's the first half of the product rule, and then we have to do the product rule the other way around. So we go e to the root x times the derivative of our first factor, which would be 3x squared. So at this point, you have taken all your derivatives and you've got the correct answer, but we could do a little bit more simplifying if we wanted. I would say it's optional just to clean this up. So ln of e is equal to 1. You could multiply the x cubed with the 1/2 x to the minus 1/2. You'd have 1/2 x to the, well, the exponents are going to add. So 3 minus 1/2 is going to give us 5/2. So we've got 1/2 x to the 5/2 e to the root x plus 3x squared e to the root x. And we might even take this a little bit further, factor out the e to the root x. You could also factor out a factor of 1/2, and you could pull out, say, an x squared. So if you wanted to factor out a factor of 1/2, then really you'd be looking back at your previous step and you'd say, well, what is 3 if I put it over 2? You could think of that as 6 over 2. And that way you've got a factor of 1/2 that you can pull out of both those terms. And let's see what that would leave us with. So that would leave us with x to the 1/2 from the first term. And then it would leave us with a +6 from the second term. So again, this is just optional simplification. For the sake of checking your work in the course pack, they may well give the fully simplified answer. You might get this answer up at the top, and we just want to be aware that they're saying the same thing. So we're going to do 3 more parts here, just continuing to practice our derivatives of exponential functions. So let's say someone gives us a function like 9e to the 2x times e to the 3x plus e to the 4x. Well, you could use the product rule here to take your derivative, but better would be to just somehow simplify your function before taking the derivative. So in this case, what we would want to do is expand first. So we're still talking about our original function f of x. We haven't done any derivatives yet. Let's leave the factor of 9 out in front, but let's multiply the e to the 2x through inside the brackets. So as we do that, the exponents are going to add. We'll have e to the 5x plus e to the 6x. And now we've got something that's set up to take a derivative. So it's going to go more smoothly now that we've got this expanded version. So we've got this factor of 9 that's just going to hang out in front when we take our derivative. Derivative of e to the 5x, we'd have ln of e times e to the 5x times the derivative of the exponent, which would be 5. Now we're going to get in the habit of not writing down the ln e every time, because ln of e is just 1. So as long as your exponential is e to the something, you won't have to write down that ln term. Whereas if you had something like 2 to the 5x, then you would have to write ln 2 times 2 to the 5x, etc. Okay, so we got e to the 5x times 5, plus for our second term, we'd have ln e times e to the 6x times 6. So in other words, 9 times 5e to the 5x plus 6e to the 6x is our derivative. So let's try another example where we have to somehow simplify before we take our derivative. Let's say f of x is e to the 3x plus e to the 4x over e to the 2x. We'll think about how to simplify that. So here's our original function f of x. What you can do is you can bring the e to the 2x up to the top, but it's now going to have a negative exponent, just representing that that came from the denominator. So take this e to the minus 2x and then multiply it through with everything that was in the numerator. We can multiply it through. So as we multiply through, the exponents are going to add, and we'd have e to the x plus e to the 2x. So that's our original function f of x, and then from there, now that we've got that simplified, we can think about taking our derivatives. Okay, so derivative of e to the x, that's going to be ln e, which is 1, times e to the x, times the derivative of the exponent, which is 1. So derivative of e to the x is just e to the x. Plus, to take the derivative of e to the 2x, you'd have ln of e, which is 1, times e to the 2x, times the derivative of what's in the exponent. So we get 2e to the 2x. And there's our answer there, e to the x plus 2e to the 2x. All right, let's try one more example along these lines where we simplify before taking our derivative. So let's say f of x is 4e to the 7x all squared times e to the 6x. Okay, so let's work on getting f of x simplified. The idea is we want to get this into a form so that it feels easy to take our derivative. So let's think about squaring this first factor here. The 4 will get squared to give us 16. And if you square the e to the 7x, remember that when you're raising something with an exponent to a power, the exponents will multiply. So it's e to the 14x. Or if you think of that differently, you're multiplying e to the 7x with itself. So e to the 7x times e to the 7x, the exponents will add to give you e to the 14x. And that still needs to be multiplied by e to the 6x. So let's do one more step of simplifying before we do our derivative. It's 16e to the 20x is what we've got there. Okay, so now that feels like something that's going to differentiate nicely, and we can do our derivative. So f prime of x, we'll keep the factor of 16 out in front. For the derivative of e to the 20x, we'll say it's ln of e, which is 1, times e to the 20x, times the derivative of the exponent. So overall, if you multiply the 16 times the 20, we get 320 e to the 20x. So that's our video on taking derivatives of exponential functions. Thanks for watching.